Good evening to one and all, and welcome to our seventh weekly discussion session for the Physics of Nanoscale Devices NPTEL course. As always, my name is Jyotishwaran. I'm a PhD student from the Department of Electronics and Communication Engineering, IIT Roorkee. So, in this week, we shall be continuing essentially from where we left off, and we shall finally come around to summarizing the notion of conductance and mobility in the Landauer transport model. So, last week, what we had done is we had considered the idea of a ballistic, essentially, not just last week. So, what have we been looking at previously? Just a minor recap. So, in the previous couple of weeks, we have been considering first the notion of modes in a ballistic channel. And then we spoke about the diffusive limit. So when we considered the diffusive limit, we primarily discussed the transmission coefficient, T of E, and subsequently, we also used all of these quantities to define the ballistic conductance. So we saw this for the case of zero temperature, low bias, and we also saw the general high bias case where we found out that oh no, we did not look at it for the high bias case. We've only seen it for the low bias cases. So for the low bias cases, we found that these current integrals and the conductivity integrals can be written as conductance integrals can be written in terms of the uh, known standard Fermi integrals. Properties of these quantities have also been presented, and we have a rough overview between the lectures and these sessions. We are kind of we know the basics of it, some essential properties. So we are finally going to bring all of these things together and define the classically relevant quantities of conductance and channel mobility, carrier mobility, and we shall finish and wrap up the Landauer transport model and see how this model corresponds with the classical macroscopic Drude-Sommerfeld model for conduction, which is what we use for long channel devices anyways. And after that, we shall be spending some time understanding the idea of realistic 1D and 2D channels, because the point is, what do I mean by realistic? Bottom line is even a single atom. So, oops, even a single atom, it's not a zero dimensional object, it's not a point object, it has a finite volume. Like we have the volume distribution for the electron, we have orbitals, and so on and so forth. So, even a single atom is in theory a 3D object. Not in theory, in reality. It is, oh God, why am I writing 3D theory? Yes, a 3D object. So then what do I mean by a 1D channel? What do I mean by a 2D channel? Now, the idealized notion of this was seen in the previous weeks where I said this 1D and 2D essentially talks about the unrestricted motion of electrons along either one direction, two directions, two linearly independent directions, or zero directions, or all three spatial axes. But here we shall see what the actual effect is when I take a material and I treat it as a 2D material or a 1D material, 1D channel. Then what are the other issues that will not issues? What are the other features that will show up, and what are the things that I should consider while using such devices? And in that, we shall derive the dispersion relation of these uh, realistic channels. We shall also briefly look at the density of states, and then through that, we shall try to arrive at the notion of subtones. And that will be the uh, content for today's session. On top of this, I shall also be spending some time addressing a couple of questions I saw in the forum. They are from 2 weeks ago, but nonetheless, I shall address them here for the benefit of everyone. So, bonus topic for today is questions from the forum. Although one of the questions is relevant to today's discussion itself, so in that way, it is rather fortuitous. Uh, so questions from the Q&A forums. Okay, so beginning today's session in earnest. Now we know that the 2D conductance for a ballistic channel is given by the following example. For small biases, for a small bias is given to be this integral. Now we know how to change this into, like, I'm writing it in terms of dou by dou e because I mean dou by dou e, but alternatively I can also use the relation over here. I can equivalently say dou by dou e of f of e is equal to minus dou by dou e f of e. So this is a property I can readily use and switch this. And we have actually worked this thing out for the 2D ballist 2D channel to derive the to find out what Fermi integrals are used. So this is something we have already dealt with in some detail. Now, when we go to the diffusive limit, so what is the diffusive limit? What does this mean? So this essentially means, so what does the diffusive limit imply? So the diffusive limit essentially implies the following: lambda of E, which is essentially the mean free path of the electron at any energy, becomes very small when compared to the length of the channel. Now remember, when we are considering conductance, so ballistic conductance, if you go back and look at what was done 2 weeks ago, if I'm right, I made a rather than conductance, I should say conduction. So what we essentially said was there is going to be an initial level on the donor side, and then there is going to be a channel energy level, and then there is going to be a, yeah, I shouldn't have said donor here. It's the source, electron source and electron drain, or current source and the current drain. So the current drain is the electron source, and the current source, which is the second electrode, is the drain for the electrons. That is where the electrons get deposited. So in this system, I have a first de-excitation and then a second de-excitation. So what should be remembered is kind of the highest available ED and the lowest available ES will give me the range of energies the electrons can have. Although this integral is typically treated as an integral from 0 to infinity, it is understood that this Fermi window function, which is the derivative, yeah, so this derivative quantity here, just to refresh your memory, this is known as the Fermi window function. Okay, so this is the Fermi window function. All right. So I'm sorry, I just lost my train of thought. So this is the Fermi window function, and this kind of tells us outside of the relevant energy ranges, this quantity is going to vanish. So effectively, this integral is actually a very, like, it's integrated over a small range of energies. And for all those energy ranges, if I find out that lambda E is much, much small when compared to L, then it is said that we have hit the diffusive limit. Ballistic transport no longer becomes possible. And in that limit, I can say that the transmission coefficient can be approximated as this because lambda of E is very small either ways. And in that case, the diffusive conductance is going to be written like this. So this is a 2D channel. So remember, if I have a 2D channel, then oops, yeah, sorry. So if I have a 2D channel, what we need to remember is the current that is flowing is no longer a volume current. The current that is flowing is a surface current. So K is a surface current. Okay, so the current density, the terminology I'm using here is from electrodynamics or electromagnetism, where we consider the volume current density J or the surface current density, which is given by K. So this is essentially the charge flux that is cutting through a unit length. Just one second, I'll tell you what that is. Yeah, sorry about that intrusion. Yes. So what is happening is I have a hmm, like if I consider a small area segment, then it is the amount of charge passing through this distance per this small patch here per unit time. So that is going to give me K. And we have Ohm's law that tells us so J is equal to sigma times E vector. So this is the Ohm's law for 3D systems. Similarly, by analogy, I can also say K is equal to, so this is sigma 3D and this is sigma 2D of E. So from this, we can essentially arrive at V equal to IR because when I need to find the current, I will consider two such surfaces and look at it one dimensionally. So over there, I shall look at the integral of the electric field, which is going to give me the potential difference. So I shall get I is equal to this quantity. Uh, this is and this when integrated over that length and that area is going to give me the oh yeah. So this is J is defined per yeah. You know what? I'll just walk this back for a second. We need not talk Ohm's law just yet. I can just say that from here because that will be too much explanation. So over here, what we have is the length and the width. So when I have a 3D current or a 3D channel, then I will be looking at two areas of cross section and I will essentially look at the flux going in. So this is J in and this is J out, and these are vectorial quantities, and I is equal to J dot A. So yes, so I will be J dot A. Oops, J vector dot A vector, which is the area of these surfaces. Essentially, it's a vector because we take a direction perpendicular to this area. So if the current is flowing perpendicular to this area of cross section, it is just going to be the product of the two quantities, and this we can write as I is equal to conductivity G times V, or V equal to I times R. So similarly over here, as you can see, I will have the conductivity that is given as a const and integral multiplied by W into L. Sorry, not the conductivity, the conductance. So from this, I can identify this quantity right here. This is, of course, the quantum of conductance. This quantity is the quantum of conductance. Please refer to the previous week for what this is. So this is the quantum of conductance, QoC, multiplied by integral into W divided by L, which implies as L increases, this quantity becomes smaller and smaller and smaller. And as W increases, this quantity becomes larger and larger and larger. So we can directly identify this combined integral to be the ballistic conductance. So this is the ballistic conductance, and this like into W by L is going to give us the conductivity. Sorry, not conductance. I sincerely apologize. The whole thing is the conductance, and uh, what I have here is the ballistic conductivity. Oops. All right. So now this relation is more or less similar to, not more or less, it is directly in the form of Ohm's law, which is essentially what is derived from the Drude-Sommerfeld model. So we can see that in the diffusive limit, we have our ballistic model, which kind of reduces into the uh, like classical macroscopic conduction model. So the approximations that we take and the values that we substitute, and the special parameters that we are considering, functions that we are considering, essentially the transmission coefficient and then the mode density function, all of these quantities seem to be doing the right purpose, because in the long length limit it is giving us something that resembles what we know classically. So since we are doing a bottom-up approach, we are starting from the atomic level and trying to generalize it all the way to the macroscopic level. We can see that this particular system that we have can be generalized reasonably well. So to practice some things on this expression, let us do one example problem. So the question is, obtain a relation between the ballistic and diffusive resistance at t equal to 0k. How do these quantities depend on the length of the channel? Okay. So first things first, we know G ballistic and G diffusive. We know the conductance. Now to get the resistance, we are going to have to consider the reciprocal of these quantities. Okay. So first, what is the ballistic? And this, okay, one more thing that I need to mention. So I shall write it right here in 2D channels. So primarily we shall only concern ourselves with 2D channels. One may ask why this is the case, but by the time we look at the long channel MOSFET analysis, which will be done in the next week, parts of it should have begun in this week itself. So next week we shall be looking at the long channel MOSFET, and there the reason for considering 2D channels will become more apparent. Well, the fact is, even in most devices with 3D channels, the conduction actually happens only in a 2D layer. So if we understand the conductance and mobility in 2D channels, then we more or less understand the conduction and notions of mobility in most devices. Okay. Essentially, by most devices, I mean MOS, metal oxide semiconductor devices, and their variants, and their subsequent other iterations. So these are MOS devices, or silicon on insulator devices, or other kind of things, where we are essentially trying to treat it as a three-terminal device with the ability to act as a switch, which is essentially what we need to construct logic gates and other circuits required for computation. And that is going to be our primary focus here. Okay, so coming back, G ballistic, now we know can be written as 2q squared upon h integral m of e. Uh, you know what? Diffusive resistance at t equal to 0 and low bias. Although that is not a very strong requirement, because whatever we are going to do here actually generalizes pretty well even for high biases, although the form of the final results are going to be going to be different. So I shall just take this assumption and move on with things. So this is dou f of e by dou ef, and what else do we have? So oh yeah, I also have w. Oh, no, sorry. Yes. So times w, which I shall leave outside, and over here. So dE times the width of the channel, which is a constant, so I don't have to keep it inside my integral. Now I know at t equal to 0 Kelvin, dou f by dou ef. Again, we have derived this at least 3 times in the past in as many weeks. So I'm not going to go through this derivation again. Please refer to the previous week's stuff. So this is going to become delta of E minus EF. Okay, so then ultimately what are we left with? We shall be left with the following quantity, which implies at 0 Kelvin, the ballistic conductance is equal to 2q squared upon h integral. Oh, no, the integral will just vanish. M of EF into W. So this is the ballistic conductance of the channel. Now what is the, therefore yeah, let me also write R ballistic, which is just the reciprocal of this quantity. So we know that the reciprocal of this corresponds to 12.8 kilo, it was 12.8, right? Something to that order. Like you know what, let me just take a minute and calculate that. It's not too hard to calculate. Just give me 1 second. So this is uh, yeah. So this is 12.9, not 12.8. So this will come out to be 12.9 kilo into 1 divided by W times MEF. So this kind of tells us what's happening here. So if there is only one ballistic mode available, then there is going to be a ballistic resistance of 12.9 kilo ohms and kilo ohm. And as the number of modes increases, the ballistic resistance decreases. As the width of the channel increases, the ballistic resistance again comes down. Okay, so this is the ballistic resistance. Now, what about the diffusive limit? So the diffusive limit shall be calculated by this method. Same method. Oops, I just duplicated the slide. Should have changed the layout. Yeah. So now what is the diffusive conductance? Again, we just saw this in the previous slide. So this is once more 2q squared upon h integral in the appropriate limits. I'm going to have t of e times m of e and t of e times m of e, and what else do we have? We have, oh, just one second. Yeah, dou by dou e f of e dE into W. Now we know in the diffusive limit d of e is approximately equal to uh, L of e upon lambda. Oops. Lambda of e upon L. Really sorry, I switched the symbols. Lambda of e upon L. So then I can take the L out. And now what we have to remember is the following. Now at T equal to 0 Kelvin, this thing will come out to be EF. So again, this quantity we know to be delta E minus EF. That is a known fact. E minus EF. Oops. Ah, so then this is going to give me, I'm just going to write the final answer. So the ballistic resistance, or sorry, the diffusive resistance is going to be again the same 12.9 kilo ohm into L divided by W lambda here and MEF. So this is the primary difference. So, okay, so this is the quantity. Once again, increasing W will indeed reduce the resistance, and the more modes we have at the Fermi level, the lower the resistance is supposed to be. But notice that this is multiplied by lambda at EF. Lambda is the mean free path at the Fermi level, and this length is always smaller than this length. So now there is a length dependence, and I'm dividing a larger length by a very smaller length. So there is going to be a very large multiplication factor to this. So even though the two resistances have the same behavior with respect to the width and the number of modes, our diff, like the diffusive resistance, yeah, is proportional to the channel length. And our ballistic is actually independent. Independent of the, or rather of L. I'll just say. Okay. So, and what is going to be the ratio of these two quantities? What ratio should we calculate? Ratio between ballistic and diffusive. So, ballistic resistance R BLL divided by diffusive. Oops. Sorry. So I have R diffusive. Okay. So this is going to be this quantity, the previous quantity divided by this. Everything is going to get cancelled out, and what we shall have is just this. Uh, yeah, or so it's going to be, so there is an L in the denominator and a lambda, yes. So this is the ratio. Let me make it a bit more clear. So this is the mean free path ratio between the mean free path at the Fermi level and no lambda below. So this is what we have at T equal to 0 Kelvin. Now let us try to do the same question for T not equal to 0 Kelvin, because that is also an interesting thing to see. No, 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 no. No, no. Just give me the blank layout. Yes, and I need to close this. Just 1 second. Apologies for that intrusion. Yeah, sorry about that. As I was saying before, I was interrupted. Yes. Uh, yeah, I should have said apologies for the interruption because the intrusion was done by somebody else. I did not intrude upon anyone. So apologies for the interruption. And yeah, so let us look at the same ratio at t not equal to 0. So at t not equal to 0, what do we have? We have g ballistic, same integral, but now this is not going to be a Dirac delta. Sorry. Now this is not going to be a Dirac delta function. M of e. AF dE into W. Now, this quantity, the Fermi window function, we know that integral 0 to infinity dou f by dou e is equal to -1. That implies integral of this quantity from 0 to infinity is going to be +1. So this is a window function. Now the name itself should tell you that window functions are essentially sampling functions. So if you have some signals and systems background, or even image processing, machine learning, anywhere actually. And statistics, of course. So this is a window function. So window functions imply that there is a kind of a sampling that is happening. So what is the sampling that we are doing? We are essentially considering only those energy levels that are relevant for conduction. So that is fixed by the temperature, and that will tell us where excitations are happening and at what energy I have conduction electrons or holes, vice versa, available in the system. So now this sampling function is also a probability density function. So this further implies there is a probability density function because that probability is non-zero within the window and zero outside the window. So it is every window function is also a density function, and I can normalize it to integrate to 1. Really sorry. Um, I can normalize it to integrate to 1, and in this case we see that it's already normalized. It integrates to 1. So this is a probability density function. Oops, where am I? Yes. Density function. So since this is a probability density function, like this comes with the density measure, this quantity here is actually kind of an average. Mind you, this is not the average number of modes, but this is the average mode density. So per energy level, per unit energy, how many modes do I have? So this is kind of the integration of the specific mode density function for a given energy. I'm kind of integrating it over all energy, so I have an average mode density function. So what I can say is the following: at non-zero temperatures, at zero temperature, this thing becomes a Dirac delta function and I literally sample just one single energy value. Now I have a window, so I shall sample over that window, And because of that, this quantity here, I can write this as 2q squared upon h m into w. So this is the ballistic conductance. Now if I look at the diffusive conductance, that is going to be 2q squared, oops, upon h integral. Now I'm just directly writing the ballistic limit, so this is going to be lambda of E, m of E, the window function. Once again, EF times dE into W divided by L. As you can see, this will come out to be average of this quantity, lambda times M, because I'm essentially averaging both of these with respect to this energy window. So this is kind of a product. This is the number of modes available. This is the number of modes by multiplied by the mean free path in that mode. So this is kind of a length dimension quantity, and therefore, and from that we will have uh, not from that. To that we need to multiply, of course, the quantum of conductance. So 2q squared upon h and then into W divided by L. So as before, there is a length dependence in the diffusive case, and from this I can say R diffusive, sorry, RD upon RB is equal to GB, or I was supposed to get the ratio between the ballistic and the diffusive resistances. So it should be the reciprocal of this. So therefore, R ballistic divided by R diffusive is equal to G diffusive divided by G ballistic. So this quantity is going to be, all other factors will cancel out, and what we will have left is lambda m, oh god, no, I don't want to draw a triangle, m divided by average of n into 1 over n. So this is what we shall have, yes. So again, as the length keeps increasing, the diffusive resistance keeps increasing. So this quantity, this ratio will reduce as lambda increases. And if I have a channel which has more and more ballistic modes, what we are seeing is that, like, we can actually see that directly from here. Lambda is a positive quantity. Okay, so this is a number, and this is a number greater than 0. So I can quantitatively say lambda m is greater than m. Okay, so as this quantity, as the number of modes increases, the quantity above is bound to increase. So the more modes I have, this ratio will tend to come down. So this is kind of the trade-off we have. When we are looking at geometries and when we are looking at device structures, what we should be focusing on is how long the channel is and how many modes the channel is allowing, and how to increase the number of modes that the channel is allowing. The straightforward strategy is to increase the width of the channel, because we know for a 2D channel, the number of modes is literally the number of half de Broglie wavelengths that will fit along the width of the channel. So if our channel length is increasing, we need to compensate it by appropriately increasing the width so that the ballistic conduction dominates over the diffusive conduction. Okay. So yeah, that is pretty much that. Let me, so this is since I can say, oh no, You know what? This part out. Let those who listen to it, because again, this comparison is not entirely valid. So this, as you can see, as L increases, this quantity goes down. Okay. So now we shall look at the notion of mobility. How does mobility generalize to the Landauer transport model for ballistic conductance? So if you look at the 2D diffusion, this is the, of course, not diffusion, 2D Landauer conduction. This is the general conductance, diffusive conductance equation. And the mobility, G2D can, or rather, this diffusive conductance can be written in terms of the surface charge density times Q. So that is the surface charge. So this is the number density and this is the charge density into mobility divided by W into L. So from this I can say that mu is equal to L by W into 1 upon Ns times Q into this above integral, which is 2Q squared upon H integral T of E M2D of E. I'm just going to replace this by dou EF, dou F by dou EF. Small biases once again. Yeah, I should have written E capital F. Just substitute it wherever appropriate. So yeah, this quantity is now the generalization of the mobility in the uh, like in the Landauer model. So this is the Landauer analog. Oops. Landauer model analog of mobility. So now, what does this mean? So let us take the relationship between the diffusive mobility and the mean free path for two cases. Let us consider t equal to 0k and t greater than 0 Kelvin. So at t equal to 0k, what happens? This window function once again. Now we can quickly do these things. So 1 t equal to 0k, we know that the window function dou f upon dou e f is equal to delta e minus ef, and let us also assume that t of e is lambda e upon l, just for the sake of simplicity. So over here we can readily see that the L and L terms are going to get cancelled. So what are we left with? We have mu 2D, the 2D carrier mobility, which will be equal to 1 upon W, and this quantity of Ns, we already know how it relates to the Fermi energy, the Fermi wave number, and we can use that if we want. You know what? Let us use that. So that will actually give us a good. So 1 upon Ns, 2Q upon H. H, the Planck constant, and then sorry, into this integral, which is now going to be just lambda EF multiplied by M2D of EF. So, you know what? I can substitute that once again by the de Broglie wavelength. So, this is going to be lambda EF into W, and those are the only quantities here. So, by lambda EF divided by 2. So the lambda and lambda cancel out. As you can see, many of these quantities will cancel each other out, and we will get a rather interesting value for the electronic mobility in a 2D channel at t equal to 0 Kelvin. Okay, so these two cancel out, and then now Ns I know is, sorry, yes, kf square by 2 pi. Ns is equal to kf squared upon 2 pi. So from this, I can substitute. Now kf itself is 2 pi and kf is 2 pi by lambda ef. So just substituting that, I will have 2 pi by lambda ef squared, and that is ns. So I will take the reciprocal of that, which will give me lambda ef squared divided by 2 pi. So we have 1 upon w into lambda of ef squared upon 2 pi into 2q upon h into 2w. So cancelling out all the relevant quantities, ultimately what we shall be left with is mu 2d at 0 Kelvin. Actually has a very strange looking form. It is actually the square of the de Broglie wavelength for some reason, by pi h into q. And you can see that the dimensions will also more or less agree in this case, because the conductance, just to go back here, or the conductivity to be more precise, is just going to be the charge into the mobility. So the mobility is a quantity that will have velocity per unit length as the unit, you know, velocity per, yes, unit length as its units. And you can see that that is actually the case here, because this is length square and h has dimensions of angular momentum. So this is going to be mass into velocity into uh, sorry, sorry, apologies. Since this is going to be the conductivity, this quantity into the voltage should give me the uh, current. So if you take that and if you do the dimensional analysis here, you will find out that this quantity here actually fits the dimensions. So this gives us the exact mobility of an electron in a 2D system at 0 Kelvin. So once again, as you can see, this ballistic property of the channel and our bottom-up approach is kind of connecting the conductivity, the mobility of the device to an actual physical quantum mechanical quantity, which is the de Broglie wavelength at the Fermi level. Now, what about the second case? Let me duplicate this guy. Yeah, so we are looking at the second case now, which is t not equal to 0. So in this case, oops, mu 2d is L upon W into 1 upon ns into q. I can cancel the q's out. 2q upon h integral. Now, of course, I cannot integrate the things away willy-nilly. So I will have lambda of e into 2w by lambda of e ef times dE into 1 by L. And now you'll find that the result here is actually stranger still. So now the lambda E and lambda E here will cancel out, and I'm just going to be having a constant here and this window function which I'm integrating. So I'll just get 2W by L. I'm going to get a factor of 2 out of this. That is all. So this is, in spite of the very complex looking form of this, apparently complex form of this integral, we are left with 2Q upon H into, yeah, so these two cancel out, 2W upon L. So this is going to be, everything cuts out, and we shall have 4Q upon NS into H. Is that correct? Yes. Indeed, it is. Yeah. So this is what it is. And you will find that this is actually close to the classically evaluated value. So this is Q upon like charge divided by volume. So this is going to give me, so this is number per unit volume. The quantity jumps up here, and then again you can do the dimensional analysis and see that even this is, the correct dimensions. And here, no quantum mechanical quantity other than the Planck constant itself is appearing. Wait a second, just 1 second. Did I miss anything out here when I was doing that? No. Yeah, all is well. So, yeah, this is what we shall get. Or alternatively, I need not have done this, and I could have just written this as average of lambda times n. So, and you can see that that lambda times m is just going to give me twice the width, which is what it's supposed to be, because at every for every lambda e, the number of modes is the width of the channel divided by lambda e. So if I multiply the two, I'm just going to get twice the width. So this integral, although it looks very complex for a 2D channel, this integral in the ballistic limit, sorry, in the diffusive limit, is actually reduces to a very straightforward integral, and we will have this as our uh, diffusive mobility at high temperatures. So over here also it comes out to be a constant depending on the material, which is the charge density. And typically we know that the mobility depends only on the material parameters, like the properties of the material themselves. So this is mu 2d. So just know the forms of these integrals. The takeaway point here is know the forms of these integrals, look at these analogies, remember this, and depending on the material that you have, depending on the density of states and properties that you have, go ahead and evaluate these integrals. But typically the questions that are given will be for elementary cases where either t will be 0 or the bias will be very small. So most of these integrals also you can evaluate. And in the case that you are not able to evaluate, you will kind of leave it as a uh, Fermi integral. Yeah. So wait. Oh, the ballistic mobility. Yes. So this was the diffusive mobility. Now we need the ballistic mobility. Now again, the ballistic mobility, we are going to use the same analogy, because what we should remember is that there is no such idea of ballistic mobility for an electron, because we are considering a quantum mechanical transport when we are considering ballistic transport. Like there is uncertainty principle, and I actually don't know where the electron is at any given point in time. I just know it is traveling from one end of my channel to the other without collisions. So this notion of mobility itself is very loose. So accordingly we should proceed with caution. So once again, this is L by W into 1 upon QNS into the ballistic mobility, oops, H integral M of E. Now you will see that there is a twist. Remember, yeah, you know what? I'll just finish the problem and then it should become apparent. EF, DF, DE, not DF, into W. Yeah, wonderful. So now what is going to happen? And here, just assume T not equal to 0, like, this is the generic case. So now what we are going to have is L into 1 upon ns into 2q upon h. Uh, just 1 second. Did I mess something up over here? There has to be a factor of W outside. So M2D is uh, D of E, yes. So W times that. So there is a W in there already. So yeah, yes. No, no, this is correct. So we shall be left with this quantity now. Our average modes again starts coming into play. And now this will tell us, so let me just bring the things together. So this implies new ballistic 2D. So this is a very strange quantity because typically when we consider macroscopic, like conductor mobility, charge carrier mobility, it is it's a fixed parameter. It does not change if I make my material larger or smaller. It may change with temperature, sure. It may change with the internal structure of my device, as we have seen here. Like, if we introduce, as we are going to see here. Sorry, we have not seen that yet. So typically, the only thing that can change mobility is the charge carrier concentration itself or the temperature. These are the only two quantities that can change it. But here, as you can see, the ballistic mobility is going to be L times, or rather 2LQ, 2 into L into Q divided by, why write too many multiplication symbols, 2LQ divided by NS times H into this quantity right here. So as you can see, the ballistic mobility increases with the length. What does this mean now? Like, does this mean that the ballistic mobility will keep on increasing as my channel becomes longer and larger and larger and larger? Well, yes, it kind of will. But what we should notice is that even though the mobility seems to be increasing with L, the conductivity will drop because I will need to include my transmission coefficient here. Like, I have taken only the ballistic limit where T of E is equal to 1. Going back to this expression, this is the only relevant form of, yeah, so coming back, this anomalous looking object. So this implies mu 2D ballistic. So does this imply this? This is proportional to L? That it will keep increasing with L? Is this true? The answer is actually no, because the notion of mobility for a ballistic channel is very poorly defined. So, here it is understood that this quantity L to consider this expression, I know that L has to be much, much smaller than lambda of E. I know it is the case. Therefore, this is not a quantity that can be varied. This is a quantity that falls in a very, very, very small range. So L is not a free variable, not a free variable. So, or rather, I can just say very small. So since this is very small, in truth, the ballistic mobility, again, if you substitute an appropriate channel length where the ballistic limit holds, then you will find that the mobility that you are deriving is more or less comparable to the macroscopic mobility. It will be slightly more, yes, but it is going to be more or less comparable. Okay, so yeah, that is that for the discussion of mobility and uh, uh, conductance in the Landauer model. So, be prepared to look at problems like this, although many of the questions are going to be conceptual. Nonetheless, practice questions along these lines. So, we are at the halfway mark at this point. Now, let us look at a realistic 1D and a 2D ballistic channel. Like, what is a realistic 1D and a 2D channel? Now, these realistic channels are known as quasi 1D channel or quasi 2D channel. So these are quasi materials. So what do I mean by a realistic 1D or a 2D channel? This is what I mean by a realistic 1D or a 2D channel. Okay, so then this extends this way. Oh, yeah, with enough practice, I can now kind of declare that I'm half decent at drawing these diagrams. Turns out PowerPoint has a line snapping feature, so I am using it more or less properly. As you can see, there is a little bit of deviation, but that's fine. So now the axis convention for this is going to be the x-axis, okay, and then that would imply this quantity, or I mean this direction here is the y-axis, and upwards is the z-axis. So I have a material for which, and let me say this is Lx, Lx, and then I have Lz and Ly over here. So the condition for a quasi 1D material is Lx significantly greater than Ly, which is approximately in the region as Lz. So Lz and Ly should be small quantities, and Lx, one of the dimensions, should be very large. So now again, as always, we are going to consider this system as an infinite 3D well. So this is my quasi 1D 1D channel. So that is this figure. So first I shall treat step 1 is to treat channel as, oops, a 3D infinite well. So from this, what are we going to have? First, I will get the energy relation. So this is going to be nx squared pi squared h bar squared divided by 2m star lx squared plus ny squared. You know what? Assume, just for simplicity's sake, Ly equal to Lz. Okay, these two are equal numerically. Okay, this is not a hard and fast condition. Everything that we are going to do here holds even if those two lengths do not match. Okay, so ny squared times similar quantity 2m star Ly squared plus nz squared y squared h bar squared divided by 2m star Lz squared. Now I know these two are equal, so let me call these two quantities over here. Let me call these two quantities ED. Now, what I can say directly by observing this before I do anything else, I can automate and let me say this quantity here is EC. Now these are not some conduction band or donor or whatever, you'll see what these are. Okay, so first thing I can say is ED is significantly larger than EC. Because Lx is very, very large, this quantity here will be very, very, very small. Now, what we need to understand is delta E, essentially the difference between two discrete energy levels. Two neighboring energy levels. Levels, we know this to be 2n plus 1 between level n and n plus 1. So let me say this is n comma n plus 1. This is the difference between these two energy levels. This is going to be this multiplied by ED or 2n plus 1 into EC. So depending on which quantum number increases by 1, if nx increases by 1, it is going to be, so I will write that also here. Ny comma nz increases, here nx increases. I hope you can understand this. So this is the point. Now what we can notice is, I will move to the next slide. So if nx goes to nx plus 1, delta E is approximately 0. It's going to be very small. Okay. However, if ny comma nz respectively go to ny plus 1 comma nz plus 1, either or. I'm not saying both of them. So this is or, you know, or yeah. Or you know what? I will just say ny goes to ny plus one, or nz goes to nz plus one. Both these cases, delta E is definitely greater than 0. So what I can say is that this energy corresponding to nx, corresponding to the x-axis momentum, like as we these quantities as we have seen in the 1D infinite potential, well, these are essentially just p squared by 2m. So you know this is analogous to p squared by 2m, 2m star to be precise. Now, along the x direction, momentum is more or less continuous. Energy is not quantized. So, along x direction, momentum is continuous. And here, along y comma z directions, momentum is energy is quantized. So, from that, I can finally say E is equal to h bar squared kx squared for 2m star plus ny squared plus nz squared times ED. So this is my dispersion relation. So this is the dispersion relation. Now, yeah, so this is one part. Yeah, I of course need to clarify here that kx belongs to r plus. It is a positive real value, continuous, and nz comma ny belongs to z plus, positive valued integers only. So this quantity only positive valued, which implies 0 is not there. Okay. So if I say z plus, it is 1, 2, 3, so on and so forth. Because 0 is neither positive nor negative. Just 1 second. Yeah, I'm back. So this is the dispersion relation. Now, how do I find the density of states? That is the second question. So this is part one answered. Okay, so this right here is the EK relation. Now it is no longer just the EK relation. There are associated n parameters as well. So if one were to try to plot, oh God, what's with my lines? Oh no. I mean, I was just happy that my lines were looking okay. Yes. Yes. So this is the dispersion relation. Now there are actually three parameters connecting this. So before we go to the density of states, let us plot this for a second. Okay. So, so how is this going to be? Remember, what is now the lowest possible energy this system can have? Kx is a positive real quantity. It can go as close to zero as possible. But nz and ny, they cannot become smaller than 1. So the lowest possible values they're going to have is 1 comma 1, which implies, first things first, I can directly write this here. This implies E min is equal to 2ED. It cannot be smaller than this. Therefore, how is my EK plot going to look like? EK plot will be something like this. And in fact, K can be negative also. It doesn't only have to be a positive real quantity. Okay, so yes. Okay, all right. So this is E, and this is K, and I know the minimum energy is going to be over here, which I shall call 2ED. There cannot be an energy state with energy less than this because of the quantization. So this is the very first impact of having a realistic finite dimensional channel. Previously, we assumed that the energy can go all the way down to zero, but that is not true because as we have been discussing since week one, I cannot arbitrarily confine a quantum particle in one direction and say, okay, it will be fully static. It cannot be because I've confined it so much due to the uncertainty principle. It will gain, like due to quantum fluctuations, it will gain some inherent kinetic energy. And that is essentially what we are seeing in the form of 2ED. Okay, so from this, I'm going to have the first EK relation parabola, which will look like it is going to touch this line. Oh my god. Yeah, I'll do this. Oh, yeah. This is a parabola, please, kindly. No, I cannot accept that. As you can guess, my curve drawing skills are still irredeemably bad, as they have always been. So, this is a parabola. Now, the next energy level it can have is when one of these goes to 2, either this or this, in which case it is going to be the minimum possible energy is going to be 5. So, I will jump up 2 notches and I will go somewhere over here, 5ED, and I will have a similar parabola. It's essentially going to be parallel to this. It is just going to be shifted. Okay, so it's going to go up like this. And then at the next, so I will have successive parabolic bands. Is going to have successive or successively upward shifted. In fact, here the k is just kx. Okay, like that must be apparent. Effectively, this behaves like a 1D system, but notice, which is essentially the 1D, because if I had a 3D system, I will a 2D system, I will have kx and ky. But since this is only a 1D system, I only have a kx, and the EK diagram that I'm getting looks very much like a 1D EK diagram, but I'm getting many, many of them. And there is going to be an infinitely many ladder of these as we rise. So essentially what this has done is upward shifted parabolic, plural for parabola. Okay, so what does this mean? This means that the number of energy states available at a particular energy level is also increasing, because notice at this energy level, I have one, let us say I draw a line here. Okay, now previously for a 1D system, I would have only had one state here and one state here. Now I have one state here, one state here, one state here, and one state here. Now I have four. So this implies more degeneracies because multiple states have the same energy levels. Okay, as E increases, because if I choose a high enough energy, multiple such parabolae will cut through it. Okay, so increases. So this should automatically indicate that the density of states is also kind of going to rise. Now, let me address, I'm going to take a couple of minutes to address a question that was raised by one, like a student in the in the forums. So I'll just take that, take a moment to address that. Okay, so essentially, yeah. So the D1D of E. Okay, so let us look at the 1D density of states. We write this as, oops, 1 divided by pi h bar square root of 2m star divided by E, or if we are considering in the conduction band, we will write it as E minus EC. This is how we derive the density of states. Notice here that we are essentially considering a level to be the zero energy level, and from there we are considering the dispersion relation and the EK relationship, and then deriving the density of states based on that. However, what we should notice that this is only for E greater than EC. For E less than EC, this quantity does not hold. For any E less than EC, I will come into the band gap. So the density of states has to become zero for E less than EC. Okay, so, and that is actually realistic. As you can see, even if I don't consider the conduction band minimum or whatever, for a realistic 1D material, I'm seeing that the lowest possible energy is actually not E1, it is ED here. Okay, the lowest possible energy an electron can have in the system is 2 eD, cannot be below that. So below that energy, there should be no states available. Okay, so I need to modify this function in general. So d1d of E, therefore the correct representation. So yeah, let me just, yeah. So this is a quick side discussion for those who are only reading these things. Okay, because this is in the band gap. So now how do we ensure that these quantities are kind of satisfied? Remember, I spoke about the theta function. Now, what was the theta function? So theta of x minus x naught is equal to 0 if x less than x naught and 1 if x greater than x naught. This is exactly what I need. If I have EC, then for every energy above EC, I should have this function, and for every energy below AC, it should vanish to 0. So this is the exact function that I need. So the accurate form of d1d is actually 1 upon pi h bar 2m star upon E minus EC whole raised to the power half into the theta function, which in some notation, so this is equivalently written as the Heaviside step function. Okay, so the unit step function or the Heaviside step function, so I should just write this as h of E minus EC. So this quantity is the step function, unit step function, or I like giving homage to people who came up with these things. So this is the Heaviside step function. So Oliver Heaviside was a mathematician and also technically a physicist. So he did considerable amount of work on Maxwell's equations and their applications. And he was also influential in establishing what we presently understand as linear time invariant systems and the Laplace transform techniques, so on and so forth. So all of those are, the contribution of Oliver Heaviside, and anybody who has done LTI systems, linear time invariant systems, will know that without the unit step function, we cannot define the solutions. The Laplace transform needs to be defined from some initial time t equal to t naught, and that will give us the positive half of the S plane and so on and so forth. So this is the Heaviside step function, and that is where this gentleman introduced this function. And some decades after this, Paul Dirac came along and introduced the derivative of this function, which is the Dirac delta function, also in some relevant areas of analysis. Later on, all of this was integrated, and we have now what is known as the theory of distributions. So this gives us the accurate form of the density of states. Okay, now wait. Yeah. For some reason, I seem to have misplaced a question. No worries. So now the second part, DOS of a quasi 1D system. Okay, so now how do we go about doing this? Remember, now the system has an absolute minimum energy, and this is the graph for that. So first, what we have to do is, first let us set up the energy axis. Snap on. Okay, so let me mark some important energy values. This is 2 ED, and then there is 345 ED, and then we have what is the next value? Both of them will be 2 and 2, so we shall have 2 square plus 2 square, which is 8 ED, so 6, 7, 8 ED. Okay, so this is nx comma ny equal to 1, nx equal to 1, ny ny equal to 1, sorry 2, Oh, no, 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 sorry, not NX, NY, NZ. Really? My undo stack was exhausted. NY, comma, NZ equal to 1. And here this is NY equal to 1, NZ equal to 2, or NZ equal to 2, and NY equal to 1. Oh, I just wrote the same thing again. NY equal to 2 and NZ equal to 1. And over here we have NZ equal to NY equal to 2. So these are the three energy ticks I shall consider. Now notice there are actually two parabolae. When I drew here, this is not just one, this is actually two parabolae because there is a degeneracy for the 5 ED minimum as well. So there isn't only one state, there are two states. So this actually gives me double the number of states. So when I write the density of states for that particular energy level, now let us see what it's going to look like. Okay, so I will have one line here, another line here, another one here. Now, eagle-eyed observers may notice that we are more or less having equally spaced energy levels. There is kind of a reason for that. So, okay, so first, the density of states for this point is going to be like this. You know, it's going to fall as 1 upon x all the way up until here. But all the way up until this line. But notice once it comes to this energy level, more like other parabolae are going to add to themselves. So this line is going to get kicked up by the line coming from here. So this will jump up. In fact, it will jump up faster because there are two parabolae here. So I will have a significantly slower falling parabola here. Sorry, not parabola, 1 over x function here. And it will kind of get to this point, and then it will get another boost from this, and then it's going to go down and down and down until the next energy level, which will occur at 10 ED. So it will kind of vary like this. So this is the density of states. Now, how do I plot this function? So plotting is done as follows. So let my minimum. Okay, so first let us identify what these are. Now you can see that there are several minima occurring here. Previously, we considered just one, conduction band edge, and for that band we defined this function. Now there are many such bands occurring. Now these are not different bands; these are essentially different levels in the same band. So these quantities are what we call subbands. So these are the subbands. So this is subband 1, this is subband 2, which is actually two subbands. So this is twofold degenerate. Okay, twofold degenerate. And this is subband 3. Okay, so now how do I write the DOS expression? So D quasi 1D. Okay, so let me call that D, let me put the Q up here, 1D of E. How do I write this? I essentially, it will depend on how high my energy is. If it is high enough, then it will have representatives from the higher subbands as well. If it is low enough, it will not have representatives from that subband. So for each subband, I will need to define the Heaviside step function. Okay. So let me, instead of writing this as 2ed, let me from now on alternatively define this as E1. Let me define this as E2. Let me define this as E3. Essentially the minima of the ith subband. I will have some EI. Okay. So from that, the density of states for this can be written as an infinite series summation I equals 1 all the way through infinity, because those are how many levels I have, 1 upon pi h bar, this is true for a 1D system, 2m star divided by E minus EI whole power 1 by 2 into the Heaviside step function E minus EI. But this alone is not enough. Remember, this has twofold degeneracy. So for each subband, I need to associate the corresponding degeneracy. How do I do that? I will alter this term here and I will write it as GI, where GI is the degeneracy of the ith subband. And you know how this line will look like if I keep on stretching it, if I look at it from a very far away perspective. All since this has like divergences, plotting this kind of becomes, actually it doesn't have divergences, because at e equal to oh no, it does have divergences, because at e equal to ed it kind of shoots up. What you can essentially do is you can truncate this plot at a very, point very close to ed, and what you will see is that this figure, when we zoom out, I encourage you to plot these things and check for yourselves. So let us say I zoom out of this. I'm not zooming in, I'm zooming out. You know what this will look like? This will essentially look something like this. It's going to be, and then, it'll again shoot up, essentially be like this. It'll be kind of like a sawtooth trail, but the point is, if I significantly zoom out, this is actually a straight line. This will actually look like a 2D density of states. Uh, I shouldn't have said that so bluntly. So I'm having this. So once I zoom it out, I shouldn't even make it this big. It will be even smaller. It's gonna be. So this quantity here. Let me name the axis. So this is d of e, and this is e. And if I zoom out significantly more, then I'm going to be left with something like this. And a slide bump like this. Slide bump again like this. Slide bump like this. See, this cannot. This will never be allowed to fall below a certain point. So this is just going to be, kicked up and brought down and kicked up and brought down and kicked up and brought down. So this is approximately, and of course there is going to be a minimum energy level before and below which nothing exists. So this is approximately flat. So the quasi density of states, the density of states of a quasi material actually mimics the density of ideal density of states of the material of one dimension above it. The example will become, so this is approximately flat. Okay, so GI is the degeneracy of the ith subband. So you can calculate these things from the EK relationship, like how many degeneracies it has. Okay, so this is kind of how it's going to alternate. So this is similar to D2D very similar. Okay, so one last problem for the day. Let me just wait a second. You know what? I shall start from there next week because that's a relatively simpler problem. I have considered like the realistic 2D material. In fact, I encourage you to do it on your own. Rest assured, I will start next week's session with that. I don't want to drag too much into it. I will take the remainder of the time to explain the other question that was raised in the forum, and after that I will end today's session. So we have now what is so so another question from the forum. So this was a request to derive Vx plus for a 3D channel from scratch. So I'll redo it. I'll kind of be quick, but I will highlight some fundamental points. So first thing, whenever I have a distribution, so if some quantity f of x is a distribution, what do I mean by distribution? Essentially, this is a density function. Okay, so when this is a density function, then I will need to, let us say I want to evaluate average of f. So how do I evaluate average of f? That is given by integral f of x d mu of x. So what is d mu of x? So this is the volume measure. Okay. Because this is a density function. So whenever I want to find the mass, I will need to multiply the density by the volume. Now, depending on my space, in general, this quantity may have different forms as we are going to see. Integral d mu. So this will give me the average value of f in this space. Now, typically when we consider flat, our Cartesian space, 1D, 2D or 3D, my d mu x, so d mu of x is actually equal to dx as defined by Newton and Leibniz for their integral functions, or for a more formal definition as defined by Riemann. So this is the Riemann integral measure. Integral measure, where essentially I just take it as an infinitesimally small line segment on my x-axis. Okay, but this is not true for every coordinate system or every space, in fact. So now let us consider the spherical polar system. Now here, even before I start deriving this quantity, let me just clarify one or two things. So in a spherical polar system, the primary axis of relevance is of course the z-axis. Okay, so I will have my x, y, and z axis. Z-axis, and if I have a vector over at r comma theta comma phi, then however, how is theta measured? Theta is essentially this angle between the z-axis and Then I take the projection of this and I will take a circle, and this angle from the x-axis is going to give me phi. Now notice that what will happen if I increase this by just a little bit in every direction. Previously, when I had my Cartesian coordinate system, a finite volume element is a cube. Okay, but in the spherical polar system, it is actually a small sector of a piece of a sphere. So the volume element dv or d mu for my space is now going to be like this. It is going to be wait, let me try to do some justice to this. Okay. How do I draw this? Yeah, I'm going to need this. Okay, and here is yes, this is how it's going to look. And yeah, so this is the quantity. This right here is the quantity whose volume I want to measure. And similarly, this is going to go inwards, and I'm going to have this, I'm going to have this, and this, I'm going to have this. So this is a chunk of a sphere. Okay, now I can get rid of this. Now, what are the dimensions? I can actually approximately treat it as a cube. But now, what are the dimensions of this cube? Along the radial direction, this is going to have length dr, which is an infinitesimal increase in the radius. And this arc length is actually going to be r d theta. And this length is going to be r sine theta d theta. That is, theta is the angle by which I'm varying, sorry, not d theta, d phi. Essentially, to get this, I will make a small theta variation along the z-axis. So that is going to give me the r d theta. Then I'm going to sweep it along the xy plane. When I do that, the sweep is given by this radius, not this radius. So it is not d theta there. Sorry. This is d phi. So therefore, this is equal to r squared sine theta d theta dr d theta d phi. So the volume measure actually becomes larger and larger and larger as I'm moving farther and farther and farther away from the origin. And it becomes smaller and smaller and smaller as I'm moving closer and closer and closer to my origin. So the Riemann integral dx or dx dy dz is a constant measure. Wherever I take it is the same volume. I'm partitioning my space into equal volume parts. Here I'm actually not doing that. I'm partitioning it into like unequal chunks. Okay, now let us come to the problem proper. So for a 3D channel, 3D ballistic channel, what do we have? So what we have is the following. So I have a, oh God, please don't draw arrows on your own. Yes. Just this is enough. I'm not going to bother with completing it. Take any point. Now, although this is what I take as Vx, for purposes of my integration, I'm going to define a local spherical polar coordinate where this axis is the z axis. Okay, because x, y, z, they're all interchangeable axes. I just need a convenient representation of my velocity. Since it can have three-dimensional movement, spherical polar coordinate is a good choice. So this is my z-axis. So if I have a v vector here, or let me use a different color so as to avoid confusion. If I have a v vector over here, then the angle it makes with this is going to be theta, and if I consider the completion of this space down here, then I will take the projection of this vector and that will give me my phi. Now for this, for my velocity to be in the net positive direction, it needs to move from left to right. This is my x plus outside. This is my x plus direction. This z is locally defined. Okay. This is not a global coordinate system. This I'm just defining over here to have a good notation. That is all. This x and y axis here, they are not the same as this. This is the global. Over there, I'm just defining a small coordinate system which I will rotate and move all over this plane to define my velocities. Okay. So then what is my horizontal velocity? It is going to be v cos theta. So v plus vx plus is going to be v cos theta. Okay, now this is the quantity that I need to take the average of. So I will have integral vx plus, this is going to be integral v cos theta. Now, how many parameters will I vary? There is no r here. So for a unit sphere, sphere, I will have the differential area which is equal to sin theta d theta d phi, because r squared and dr will kind of vanish. So that is the area unit on a unit sphere, and that is all I need here, because I don't particularly care about the length of the vector, because I'm kind of moving that. I'm not considering any variation in the velocity itself. I'm just looking at the angular position of the velocity. So I'm averaging over the units, the surface of the sphere. In fact, I'm averaging over one hemisphere in this region. Okay. So this is going to be a double integral. Now, what is the value of theta? Theta can be perfectly along the z-axis, or worst case scenario, it can be fully perpendicular. So theta varies from 0 to pi by 2. And phi can have the full spread. The projection can rotate every which way. So this is going to be from 0 to 2 pi. V cos theta, sin theta, d theta d phi. And below here, we are going to have the integration of the volume measure alone. So 0 to pi by 2, 0 to 2 pi, sin theta, d theta, d phi. This is what I have down here. Now the 2 pi, the phi integral is fair enough because this thing has azimuthal symmetry. Like if I rotate this channel object by this direction, so it is no change. Like essentially rotating about the x-axis will not change my system. It's going to change the orientations, but effect like my current is not going to change as I rotate it. That is my assumption. There is no angular dependence on the velocity also. Okay, so yeah, I'll mention that here. V has no angular dependence. So the V actually jumps out of this integral. It does nothing. Okay. So then from that I shall get the above integral is sine 2 theta by 2 d theta, which is from 0 to pi, 0 to pi by 2. So 0 to pi by 2 is the same as sine theta going from 0 to pi. So that integral is going to be 1. So the numerator is going to be 2 pi into v divided by 2 whole divided by this quantity here. Now sin theta d theta is going to be 1 and not 1 by 2. So this is going to be 2 pi. So these two quantities cancel out. Vx plus is equal to v by 2. Which is, conventionally what we expect. If a particle can randomly move in every direction, on an average, if I'm asking what is the probability it's moving along a particular, what is the average velocity it can have along a particular direction, it is going to be half of the total velocity. And this is true for any axis I choose. If I choose any direction and I ask what is the average velocity along this, it's going to be half of that. Uniform distribution of velocities and all of that, like that is the reason why I'm assuming the velocity is uniformly distributed across all angles. There is no angular dependence. So the velocity has to be v by 2 because there are only 3 directions and I'm choosing one half and I'm asking what is the average velocity in that one half. Okay, so this will come out to be v by 2. I hope this answers the question of the person who asked it and also, clarifies the thing for others who may have had this question and have not asked this. So yeah, with that, yes, we have been going on for a while. So with that, I will bring today's session to a conclusion. Once again, I thank you all for attending and for listening. Next week, we shall begin with quasi 2D materials and move on into further topics. So I shall see you all again next week, same time. Thank you.